can start now. So hello everyone and welcome to our today's Innovation2GO webinar focusing on digital twins. The topic today is the digital twin for material and process design in lightweight construction. And our guest today is Dr. Klaus Wolf from the Fraunhofer SCAI, the Fraunhofer Institute for Algorithms and Scientific Computing, short SCAI. Dr. Wolf is the head of the business area, just one second, multiphysics. He's a computer scientist focusing on numerics, and the area multiphysics combines different simulation methods and physical principles to a structural simulation. So to this end, mathematics, physicists, engineers, and computer scientists work together at the SCAI. And my first question for today is there anyone who does not speak German? Otherwise, we could go on in German. So if you prefer English, please give us a feedback. No one, neither in the chat nor a raised hand. So Herr Dr. Wolf, würde ich vorschlagen, könnten wir theoretisch gesehen, wenn Sie mögen,
ja,
Englisch ist fein. Perfekt. Ja. Können wir auf Deutsch weiter? Oh, wait. Benjamin Weber schreibt English is fine. So he would prefer English. So
no problem. I can do it in English.
Yes. Okay. Thank you. Thank you very much. I would say sorry for this interaction. So the screen is yours, Mr. Wolf.
Okay. Thank you, Henrik, for this kind introduction. And thanks also for the doctor title, but I don't have a doctor. I'm just a Diplom Informatiker in Germany.
Sorry.
No, it's not too bad. So this presentation is a joint presentation from 4 Fraunhofer institutes. With the Fraunhofer Institute IMWS in Halle. They are material experts and manufacturing process experts. We have the Fraunhofer Institute IZFP. They are experts in sensor technology and non-destructive testing. And the ICT, they are the experts in manufacturing, especially in injection molding and the end of the manufacturing processes. And we at SCAI, as Henrik already presented and mentioned, we are mostly on the virtual side. So we are responsible for data organization, simulation, data formats, and so on and so on. So what is the presentation today about? It's the idea is to show the complexity and some ways and concepts how to realize a digital twin for a quite complex and distributed manufacturing process. In our case, that's the usage of unidirectional endless fiber tapes to be used in, for example, you see it here, seed shells in automotive domain. So I will give you a short introduction about the processes itself, the manufacturing machines to be used, the measurements which we do during the processes, and also what kind of simulation we use to complete this digital twin and complete the data used in that domain. Then the next step, I will show you some concepts how we see how a digital twin could be realized. What are the ingredients? How can it be combined? And also, third step, what are the semantic definitions, so that all engineers coming from quite different domains, including the computer scientists working in even more different worlds, so that all partners have the same meaning and same idea of the data and definitions to be used in that context. And then finally, give an update and status on the current prototype implementation and what we plan to demonstrate by these digital twins in the next few months. It's an ongoing project. It started roughly 2.5 years ago. We still have 4 or 5 months to go for the final steps, but we are quite close to a solution which can be presented. So first, let's start with the thermoplastic composites. What are they used for? Application domains are mostly in automotive area, for example, seat shells, different areas, but also chassis parts or shorter parts, beam-like structures. So anything that you can make out of these kind of sandwich structures. It's a quite efficient material, has a low density, but a high mechanical performance, and is highly adaptable to many different geometries and configurations. We already have quite efficient manufacturing processes with short cycles and a high level of automation for serial production. And we can do, when you look on the seed shell here, we can produce quite complex part geometries by combining different types of manufacturing subsystems in one part. So, for example, doing a hybrid forming and injection process for one and emerged in a combined process. Also, the part manufacturing has a high level of integration, high functionalization in it, and also sustainability and recyclability is quite good in that domain. So that is just a short background on the thermoplastic composites. What is the manufacturing workflow? If we, for example, let's go back, if you look what do we need to do if we want to produce such a seed shell for automotive environment? What does the manufacturing workflow look like? Starting point will be the fibers and the compounds coming from raw material providers. These compounds and fibers then will be used as input for the unidirectional tape line machine from Krauss-Maffei, for example, UD500. And the output will be these, you can see it here with an endless fiber tape, which has maximum width of 500 millimeters, might have a length of a few hundred meters, so that the final roll might have a size of a diameter of 2 to 3 meters, and a width of 50 centimeters. So it's a quite heavy thing. This currently is done on this site in Halle, eastern part of Germany at IMWS. They have those machines and all the knowledge to do it. And then these parts, these rolls will be sent to the ICT in Karlsruhe. They do the tape laying on these Diefenbacher machines. The result of that stacking process will be a stacked layup, which you can see here, for example. This then will be consolidated in another machine, so that you then have the laminate. The laminate then can be formed and hybrid injection molded to come into its final form of a seed shell, also having maybe metal parts included in that part. So that is the major parts of the manufacturing history. We have some steps left out here, for example, the slicing of those tapes, cutting up maybe a few centimeters in the beginning at the end. So some minor preparation parts would even happen here. They are not part here in this digital twin, but we have to be aware of these manual parts outside the automation process. When you look, or what are the details which you want to look into? If you look into a tape and you make cross section, this upper part would be a more or less ideal fiber injected fiber with the ideal fiber spreading, low gaps, low spores. It's very fine, can be used in a high quality. If you look on the lower side, this would be a worse quality of tape. It might be used in some areas where we don't have critical loads on a part, but you need to know it, and these kind of information has to be extracted and has to be measured by the sensor systems which we have implemented in the production machines for online inspection, but also for the offline inspection. And also there's cross section, but if you look in the length direction, you might have these kinds of woven waves in the fibers. That is working fine, still working fine, but if you have more complex wovings, ondulations, this wouldn't work properly in the final products. At the final part, so that's not a seed shell, but that's a roof, part of roof, but it's similar problems, similar issues. We'll have metal parts included in that part. So also we have to look on the fiber orientations, which are quite close to these metal parts, and the overmolded structure around these metal parts in the final construction. So that is the level of detail that we have to look into, because those details have an influence on the final product quality. That means during the production step, which I showed in the first slide, we have to implement and integrate many different types of measurement technologies, sensor technology, to get as most as possible detailed data out of the production process, and finally also for the final product testing. That would mean we have, for example, on the tape production machine, we have a camera system. It's kind of a stereo camera system, a profilometer to measure the thickness, but we also have infrared cameras on top and below the tape to do a thermal inspection, which also gives some first quality ideas of the produced tape. That means if that would be the produced part, that's not yet the final tape. So you see here the big gaps. In the final version, this, of course, you don't find these gaps, but they would have the cameras here, this camera here and the other camera here. They would provide these kind of images at the end during the ongoing production of the tape. If you look on the other end, on the seed shell, you might have morphology measurement systems, manipulators which can slice-wise go over the seed shell and can give you feedback of the stack information of the final product of the seed shell, which then can be compared also to the stacking information which was used before the forming of that seed shell. That means in the laminate. And then that also can be combined and compared to get a better feeling how is the input laminate, how will it be formed into the final seed shell system itself. And that will be, you can see the real parts here, the real installations at ICT in Karlsruhe. And of course, we also do simulation, virtual simulations of the tape impregnation and laminate consolidation, thermoforming, injection molding, and structural processes. That means we have quite simple kinematic tools to do the simulation of the layup. We have more complex tools to do the injection molding part, hybrid mold, injection molding for the seed shell. And also we have tools to map data from one manufacturing process to the other one to have to make use of the preloads and the history of the materials in the follow-up simulation steps. So we already have a number of simulation steps implemented, but not all steps are simulated in that detail. And that's also an ongoing work that is using of AI technologies to do a smart analytics of the data. For example, if you have enough data of the tape production, and if you have quality labels on the tape, so that an experienced engineer says this part and this kind of fiber orientation is fine, and that part is not fine, is worse, then we can use AI and image processing tools to do more automated defect detection during the online production of the systems, but also for the laying processes to get a better feeling if this kind of laying is favorable for the final product design, so that we, at the end, that is partially still a future topic, get a parameterized simulation so that we can automate the simulation and the modeling by getting support from the AI-based analytics, which is based partially also on real data coming from measurements and sensor data. So I showed you so far that we have many different sources for data, very different data also. So we have virtual simulations, mostly using AVM simulation models. We have diagnostic and online tools, online testing. We already had partially defect detection tools using AI tools. And we have access to many of the manufacturing parameters and manufacturing data itself and the organization of the manufacturing workflow. And all these data sources need to be combined in a digital twin, or it might be a digital quadruple even, so because we have more than 2 sources of data and information which we have to combine in a good way. That means we have to combine data from manufacturing, material, and simulation. What does it mean and why do we use it in our application? So at the end, we do not only want to organize data. Of course, that is one benefit of its own, but we want to use this better organization of information and data of the complete processes and parts and products to optimize the processes and optimize the products, because we know better what is happening during the single steps. So that we can enhance the details, but also the overall development process. And we want to get a multi-resolution and cross-scale, cross-stage information, not only on the highest level, but also, if possible, integrate microstructure information wherever possible and integrate that into the macro information world. And also try to get a better feeling of the interferences between the initial input of fibers and matrix. What kind of influence does this have on the final product of the seed shell? And to organize all these data and information in a good way, we need a ontology-based data integration. That means we need clear and clearly defined and well understood semantic definitions of all the data, information, formats, and so on. This should be open and extendable, and so that it's not defined for one single case, but it should be more come from a generic definition, and then we do a specialization for this case, so that we, in a quite easy way, can transfer this solution to a similar manufacturing process, manufacturing workflows, just by adding a few more parameters, definitions, and class systems. And ontology also means it should be machine readable, interpretable, inferable, so that we can apply AI-based analysis and correlation tools to get a better, even more understanding by using all the combined data, what is going on in the real world of the manufacturing. And the industrial demand overall is they need to get a better understanding, and they want to get some idea how can they organize their distributed data systems, which they probably have, the legacy systems, data systems. How can this be done? And by using, as far as possible, standard interfaces, standard rules, standard concepts, which are used and currently used in industry. So if you go back to the general manufacturing workflow, which I mentioned in one of the first slides, you want now, if you want to go to get a systematic view of the manufacturing process, we have to split the parts up into all their details, which are of some interest for us. That means, as you can see in this animated part, finally, we will have a list of details represented by those icons here, which represent the most important parts in that manufacturing process. Starting from the input here from the fibers and matrix. In the beginning, we have here the tape production part. We have here the stack laying part. We have here the overmolding part, and here we have the final seed shell. That means we have machine data. We extract machine data, all the parameters which are of some importance or might be of some importance for the data inspection from the different machines, for the tape machines, for the stack laying machines, for the compounding machines, and for the hybrid injection molding machines at the end. So we collect all these data, list of parameters over time. We collect also data from the non-destructive and online evaluation in the machines. So we have three places in the moment where we can do an online inspection. We have online monitoring sensors installed in the tape production, in the overmolding part, and in the final product inspection part. These data might be then, they might bring us results from ultrasound inspection, thermography, and other inspection tools. We have a number of simulation tools. Here in our case, currently only for the two major steps, for the tape production and for the hybrid injection molding process, where we have multiple simulation steps connected. You see here, this part is not yet simulated because we don't expect yet too many unexpected issues, problems, and so on that domain. We could do this later on. and extend the simulation world also for some of these steps here between. The system, the concept of the digital twin is open for that, but it's just a question of efforts which have to be put into the update and creation of simulation models. And we use a first approach to use data-based analytics or AI-based analytics for the inspection, defect automated, and AI-based defect detection of the tapes coming out of the tape production machines. But again, these type of database analytics could also be used in different steps here. But for the moment and for the prototype, we do it just in the first step here. So if you look on this quite complex gen overview on the workflow, we also need the traditional manual, manuals, reference books, which describe all the details of all the single steps, processes, machines, simulations. So kind of handbook or reference book, which will be updated all the time. If you change some part here, we probably have to change and update one chapter, which is describing that specific detail, and then we can regenerate a new reference book for the current installation. So also the reference books or the master book has to be flexible so that it's easy enough to exchange, to follow the replacement of single parts in the real world, so that the master book can also be generated in a fast and efficient way just by replacing single parts in that master book. So this is really a handbook for the end user and for the technical engineers in any detail to understand in all details what are the parameters about, what is the parameter range for each data, what does it mean, how is the machine built up in detail, where are the real positions of sensors in the machine, and so on and so on. So this is also still necessary in a classical way. It's right, you have to write it down and collect all information in a readable way. So far I spoke about the ingredients, what kind of information is available and will be used and will be combined in a digital twin for these processes. But that is a major question, and is getting even more complex if you look that we have engineers from the material science, which are experts in the fibers and matrix parts. We have experts for the processes, for the different manufacturing processes. We have experts for the non-destructive testing systems. We have IT experts. We have AI experts. And all these different experts, in the beginning at least, speak a kind of different language. Just imagine if you speak about temperature, what exactly does temperature mean? Just a simple word, sounds like a simple word. But before you store a temperature value somewhere, you have to know what does that mean, what is meant by this temperature. Is it just a temperature of a complete space? Is it temperature just on a single point? Is it temperature of a room? How did I measure the temperature? Is it radiation temperature? And so on and so on. And so many, even for simple temperature, you have to describe in any detail how this value is defined from a syntactical point of view and also from a semantic point of view. To come to a solution here, we started to look on different concepts, ontologies, for example, the MMC and MO ontologies as one major part for at least for the material science, which give a lot of input, also based on the material digital initiatives in Germany, so that is quite closely related. But we also look on the other side, on the big data aspects, what happens and what have to be looked on if you exchange data, like digital contracting between different partners. How can this be handled? If you look to the International Data Spaces Association, you will get an idea how in the big commercial world, how data can be exchanged and managed and organized in a commercial and legal proper way. And if you look to the classical engineering definitions coming from DIN, from ISO, ASTM, NAFEMS, and so on, they all have many different definitions, which are widely used in the engineering domain since tens or 50s of years. They are established, accepted, and well-defined. And we have, from that base, we have defined or derived and specified the MPCCI ontology for digital twins. This captures to a quite good level of detail the major aspects of manufacturing, of materials, of analytics, AI-based analytics, of data storage, what is a component, what is a product, also partially not so detailed yet now on CAD and design step formats, for example, but more details on simulation and measurement. And all the links, the semantic links between these different worlds. So if you look on manufacturing, it's about production of components and components they have to be developed and so on. That means in detail, for example, if you look on the right side, you can hopefully can see it's quite detailed. A number of sources, information sources from DIN norms, DIN EN 1560, DIN EN 127, and so on and so on. They give a lot of information about material classification and taxonomy for materials. And based on these many definitions, we define the basic class, the basic taxonomy for materials in our MPCCI ontology, so that the major definitions, and especially those class names which you use here, they follow these well-established and well-used and widely used naming conventions in many of these D norms. So that should be quite readable in the initial and on that higher level. And also the subclasses and subclasses are quite well described already here. You will find similar things for manufacturing entities. What is a manufacturing entity? It might be a manufacturing process and manufacturing systems. For the manufacturing processes, you could see coatings, shapings, formings, separatings, processes, and so on, and detail this further out. All this is already described in a very good way and accepted by many D norms and European guidelines, and so on and so on. So we use these information as input for our definitions, for our taxonomies. Same for the measurement. Again, you see many different norms which we use for the higher level organization of taxonomy. On the simulation world, you will not find so many DIN norms, but more in VDI or NAFEMS norms, which also give a quite good, at least practical guidelines how to organize and how to differentiate different simulation processes, different simulation tools, simulation models, and so on, how to do this in a quite good way, so that this is at least most widely understood by most of the simulation engineers in that world. Now, these VDI and NAFEMS are independent organizations representing thousands of engineers in that domain. So we can, and therefore we follow their definition and their ideas to organize information. So that was on the higher level taxonomy, the basic classes for information. Each of these classes, so that is quite similar to, if you know, object-oriented programming, C++, Java, and so on. You have data properties for each of those classes. If you look, for example, on the data properties for a air-coupled ultrasonic testing property, that means here it's air-coupled. You might also have fluid-coupled ultrasonic, and you might also have different types of coupling ultrasonic testings. And for all these, even just for one single case, for the ultrasonic testing properties, we need the acquisition time, the acquisition number, the amplifier type, the bit rates, bits allocated, bit stored, number of columns, date time. All those details, all these meta information needs to be stored and managed in a very good way if you want to reuse that ultrasound image at some later time, because then some days later, some weeks later, you need to know exactly when was this measurement done, what was the real object to be measured, what machine, what sensor type was used, what was the frequency, and so on and so on. All this information must be stored. This meta information must be stored and managed in a quite good way. So our ontology extended for some of these measurement technologies, extended in that detail how this could be done. So we didn't do it for all the other types, but this can be done in a quite similar way. So if you look on the first implementations which we have provided, then the implemented for other types of censored That would be quite straightforward. What we do not do is storing the real data behind. For example, for the ultrasound inspection, they use the ASTM Dacondi format because that is a big XY image, megabyte size, which should not be handled on ontology level, but should be just on ontology level, we just handle the reference to that Dacondi file, and then you can get that Dacondi image and do any kind of image processing on that tools. Similar for simulation, a single simulation results might have a size of gigabytes. So these gigabytes are not useful to be stored in an ontology, but all the metadata would have a similar level of detail should also be defined properly in the ontologies. And then the next level in ontology is to have clear definition for the object properties. So what are the links, the semantic links between different objects? That means different instances of classes. For example, a manufacturing process can alter the cohesion of a material, and it can produce a product entity. A product entity is made of material, and a measurement entity can do measures for a product entity and so on. These kind of generic class-based property relations will help us later on when we have the real data and the real instances for all these data to have a clear understanding if I want to find for a specific product entity, product entity, all the measurements which have been done exactly for that product entity which was made maybe yesterday. And for all these relations, we have predefined a number of generic relations between the generic type of classes which we had here. Any of these properties can be refined further on if you have a very specific application on your side, but that would be just a refinement, single place refinement here. But all the higher level rules still would be applicable. So what does this mean in detail, in concrete detail for our process? If we can go back to the systematic view of the digital twin, looking on the tape production part here. So we have the fibers, we have the matrix, we have the machine here, the calendar, including the components in the machine, the calendar machine, the extruder here, and so on. And finally, we get the product out of it. That means we will have the input. We will have injection granulate. That would be the class, the type definitions, and we would have roving fiber as an input. And for a concrete manufacturing process, that means for the concrete tape, which was produced on in year 2021, March, 24 of March, for that tape, which was produced at that date, so we could even add the time, the date time here. So we want to know in any detail which granulate was used, which package of granite was used for this tape produced at that time. So we have instances for the granulates, we have instances for the roving fibers coming from specific companies and so on. So that it's later on when you have the tape itself, you have tape production, and that would be the ID, the identifier of the final tape here, the thermoplastic UD tape made on that day, which was run through a production system using the roving fibers. That would be that part here, that link here, using the tape production parameters. So here you could find the manufacturing parameters of the machines, and some information on the processes and so on. So all the information coming from a class, from a generic definition, can be broken down when you have a real production. You have the real instances for each of those parts so that you finally know exactly what ingredients have been used to produce this tape, what processes have been used, and what parameters have been used to produce that tape. Similar for the overmolding part, where you have, for example, the overmolding and including the metal parts here. You have for the overmolding, you have to look on the tape production part. You have to look on the tape laying part, the laminate consolidation, the preparation parts, heat treatments, and so on. And you also have to look on the metallic insertion part. So the overmolding is has feedback, has backward links to all the single steps already done before. So for a single overmolded part of seed shell, you will find all the single steps which have been done before and all the information for these steps. And similar for the simulation, a simulation instance will have a concrete date here, day and time, so that it can be linked, also using the meta information, can be linked and for comparison to real data. And also for the measurement, these of course has to be linked directly to concrete product or pre-product, so that you have the date and time usually for these inspection data. So that would be the final way how to use the ontology to create real instances of data, and using the ontology concepts, the object properties, to link between the single data properties of a measurement data to a simulation data to a manufacturing machine parameter data set. So that was all about the way how to organize data from a more semantic or principle way level of point of view. For the end user, for the OEM, for example, we have to look, we have, as mentioned already, the different machines, the tape production machine, the stacking machine, taping machine, the consolidation machines, and the hybrid injection molding machines installed on at least two different sites. And the end user, which might be a machine driver, which might be a design engineer or materials engineer, those engineers want to know and want to extract as many as possible details on all steps. So we at SCAI, our task then was the task was to find ways to combine the different data. Each of these partners have their own data services and data systems inside their company world, and they have put some data server in front outside the firewalls, so the user and the partner can select which data will be provided for the digital twin analysis, so that they can make it's under their control which data will be put on the external visible server for those data. So we have Daconte type servers. They manage all the inspection data, the ultrasound and thermography inspection data. We have different types of SQL-based servers. We also have an own cloud system for simulation data, for example. And all those type of servers have different interface types. So DICOM, REST APIs, Database Connect, REST APIs for Django, and WebDAV services for OwnCloud, and so on. And there will be many, many more different types, typical ways of connecting databases to an integrated system. So the first way was to define the software interface layer so that we can connect and read and write data from the distributed located databases. And then we have to define the metadata, which needs to be extracted initially, at least, to know where can I find which information just by looking through the meta information. So for example, I'm looking for all the tape data which were made on that date and that time on that machine. So these kind of metadata must be made available and really fast accessible to these interfaces to the Twin Manager. And then the next step that is really reworking all these informations. For that, we installed a Sparkle endpoint at Fraunhofer SCAI to handle all these information, this meta information. That means we use a storage of triples based on our MPCCI ontology. And triple means, if you look here, a triple is really a subject predicate object connection. We would have a triple overmolding solves a model for this simulation, solves a model for this process. So any two boxes and one arrow define one triple, which are stored here, including the types and the concrete IDs of that data which is behind those instances, so that we here have a graph database. And this graph database then can be used, that's a standard technology also used by Google and all those companies to browse to the information and look for further relations between data. That means, for example, if I want to look for the seed shell produced on that March 24 and 21, and I want to see what input was used and what output was used for all the steps before that, for that seed shell. So first I can try to access the machines and read out the machine data. So then I would get access to machine data over time, and I can use and check and involve and analyze these in some way. I can also extract the initial and raw ultrasound or thermography images and try to work on this and use this for further analysis. And I can also extract high-level simulation for the seed shell itself, which was made also at some time. So that is the idea of the first idea of the digital twin, to get access to all data which is related to a specific, maybe a specific entity, a specific seed shell, which was produced at a single step. I could also ask, for example, I have a big tape. This big tape can be used and has enough material for many, many seed shells. So which seed shells overall have been made of this big roll of UV tapes at some time, if I need to know this. And we are now on the way to make this a bit more comfortable. That means we have a draft user interface on an ASCII level, but we are also working now on the graphical user interface for the system, so that you can put your request to the system and get a feedback directly in the related presentation modes here, for example, for simulation of the seed shell at some point. But that is just the user backend or user front end. The data management is the same behind. So, and that is this, the step where we are currently in. So what is good for? So it's fine to have all data organized, may help me in the future to find a better organization in future, but what is the concrete benefit for the end user, for the OEM, for the manufacturer, by using these digital twins? One point might be, if you have a feedback loop, if you do many, many tests of the final seed shell and define some weak points in the seed shell, you can look in detail, okay, for the seed shell, which material was used, which processes were used in the different steps, which process parameters were used in the different steps, and then you can try to analyze what might be the reason, the specific reason for this weak point in my seed shell, supported by different types of AI analytics tools. And then you can go back, because you know the detailed parameters which led to the final seed shell, you can improve some parameters maybe in the tape production at some time, or change some parameters in the stack laying processes. Another part might be a more local optimization, that we have an ongoing and an online monitoring of the tape production, so that we have an online inspection if during the production of a single tape, the monitoring system, the sensors see some kind of defects. They can directly control the machine, the ongoing process, and correct the parameters, so that at least only a few meters of UD tape have a defect, and then the rest is again fine. So that would be more a local improvement for using the digital twin. But anything between these local and global information usage for optimization would be a result of a good digital twin catching all relevant data in that specific process here. Okay, so let's come to my last slide. The implementation of digital twins for thermoplastic composites needs a lot of work and a lot of ingredients, a lot of expertise to be done. At first, of course, you need the interdisciplinary teams and expertise. So you really need people which can and want to talk to each other, because you want to combine technical information from quite different domains in one big data system. So you have to understand each other in a very good way. That means we have to work on a common language, which in IT means we have to develop a good ontology system which captures all definitions and data and so on in a good and systematic way. And of course, that is more on the engineering side itself. If you know what you do with the data, then it's really helpful to implement more and integrate more and more non-destructive sensors during the production line, so that you have an early feedback during production if something is going wrong, and for later also if something later happens with the final product, so that you know at least why this happens for some reason. And of course, now it's better. You can, it's more feasible how to use and how to validate CAE simulation results and how to use simulation results in the different steps of that digital twin. If you exactly know what a simulation is done for, which part and which step will be solved by a simulation model. And this also needs a flexible data management concepts and interfaces. So the implementation which I showed here is a specific implementation for these consortium here. But in principle, if you look at a different consortium, you will find different data management systems, different interfaces, different formats. The concepts are open and are open enough to give a good guideline and the ways of implementing a new digital twin for another application domain using different details of technology. The concepts are flexible enough to use it and to do a transfer to different application domains. Yeah, this here, what I showed here, that's just a pilot scale technology lab, which we have an open day tech day in springtime in May next year, where we show all these aspects in a hopefully an online running digital twin. We can all see the data during the online production. Okay, that's all from my side. Just a hint. This tech day, it was planned for 1st of February next year, but as you might know, the Corona stopped these activities. So it will be postponed to May, sometime in May. But then we will have a tech day at Fraunhofer Institute in Schkopau, in the eastern part of Germany, where you can see all those details, the digital twin, the real machines, the real materials, in real hardware and real software running. Thank you very much for your time. Thanks for listening. And if you have any questions, please let me know.
Yes, thank you very much for the presentation. And I have a first question in the chat. It is, so thank you for the interesting presentation, Mr. Wolf. How much effort is still required to implement your approach developed in this research project in real production environment? And the second question in this chat was, and what will be the main challenges be?
The main channels, let's start with the second question, will be really to find if there would be a new customer or consortium, to find the experts which know any detail about their domain and which are ready to talk to other experts talking a different tech language somehow. So the initial discussion, this took us also a few months initially to find a common language. What exactly do you want to know? What do you mean by temperature? What does this parameter mean in your machine? What is your expert's feeling about this influence of these parameters? All these non-automated but human interaction is really important in the beginning to come to a common language. And then it's quite straightforward. That's our expectation, at least, to use, for example, our ontology system to refine it in the on detail levels. So it's a different machine, it's a different sensor, but all the major relations and major data properties which we already have in our ontology should also work for different manufacturing areas. And then next step then would be for the implementation. Then we have to look on the concrete database systems. So we already have some solutions for these 4 or 5 typical database systems. If there's another database system, okay, then we have to look how can we interface maybe to an SAP-based data system and communicate to this. This is a bit dependent on the specific database and interface technology. Might take some weeks or months to get these interfaces running. But then we would have at least the first solutions to get all the different databases communicate to each other, set up a triple server. This is also quite straightforward and mostly automated if we have the ontology. And if we have the ontology would be the generic description of data, but you need to know the native definition of data in your own data system. If you have tabular-based system. What does table column 1 and 2 and 3 and 4 mean? And then we can find some kind of translation of these specific customer-specific data organization to a generic organization, which we have. This might take also some weeks, depending on the size of data, but that are mostly single sets of steps of translation from a specific implementation to the generic concepts which we have on our side.
So regarding to the high complexity of these processes, I think if I count all the time you mentioned, these are a few months. So I think it's quite fast in the end.
At least a few months to get a first, yeah. In total, it's the detailed. That would be at least good enough to have a prototype. Mm-hmm. If you want to have a production system running, you can put a factor 2 or 3 or 4 in it, I guess.
Okay.
It's would be just a first prototype to see if it works at all. There might be some hidden challenges that we didn't see in the beginning. Yes.
Yes, but I think at first sight you will be of service if you try to get all the experts on the same level and to enable the exchange, because as you already mentioned, they are highly specialized in their fields, but they are not specialized in the other fields in the end. So
yes, if you would have to run a project, a specific customer project, the first phase would really be have a lot of discussion with all those people and get an understanding. Yeah. Then we can decide how to implement.
Okay, to the other participants. Oh, okay, here's a raised hand. Just a small hint. If you have questions, just raise your hand, or otherwise you can type your question into the chat and then I will read them out. But Bernd Engelkamp, you raised your hand.
Yes. So thank you, Mr. Wolf, for the nice talk. Regarding the experts, you mentioned also AI experts.
Yes, yes.
In which terms do you use AI methods?
For example, one case which we have is the defect detection of the tapes during production. If you are a manufacturer or process expert for UD tapes, you look on that tape and you see, okay, this is wrong here. This fiber orientation doesn't work properly. But then this has to be translated somehow. You have, if you want to use an AI system, you initially need at least a number of test images which can be presented to the AI system so that this system can learn. And all these images have to be labeled. So the expert engineer, the human engineer, has to label and mark local points on that tape. That is a good region, and that is a bad region, and that is a B or C quality type region. And then the AI system can learn and be trained if there are enough images and test cases so that it then can be used as an online inspection tool later on. But initially, of course, you need enough test data where the AI system can learn from.
Okay, so I suppose it's the same thing like deep learning?
Yeah, for example, this way. If it would be these kind of image processing, then it would be these kinds, yes, neural network systems, yes.
Okay, thank you.
Okay, I have another question because you mentioned there's a lot of data in your product process. And so you will, in the end, you will have one file per product, per produced part. Is that right?
No, that's definitely not.
Oh, I'm sorry.
Oh, that's a good question. So maybe this one here. Mm-hmm. So what we would have many different big and small files. For example, here on this server, we would have all the sensor data, online and offline sensor measurement data as separate files. Each file might have a few megabytes if it's an image, for example, might have a few megabyte size. Here we would have a good number of simulation results as separate files, but all should have good metadata information so that we need from outside can fast see, okay, this simulation was done for this purpose by this author at that date using these codes and so on and so on. So all the data initially are stored as separate files, as separate machine parameter files and so on the local database system. But the meta information must be clearly defined so that it can be extracted by that manager. What we have here is only meta information collected, which is just a compressed few parameters 10, 20, 30 parameters per file, which you need to know to have a fast overview. What is going, where can I find which details? And here again, this graph database is just a connection of these metadata between the different files. The heavy data are still separated and stored locally on the different sites and only downloaded when I need them.
Okay, but it is what I meant is it is referring to one part. So also the references. So you have one file with all the references. If you, for example, you find some mistakes in the production process and the fibers aren't properly mixed. No, if you, like you had in this picture, that they were not in one layer, but there were some more on one point and no fibers on the other point. So you will be able to, so you have references for one product in a file, and you can say, okay, if something is wrong and the product is, the end product is not, has not a good quality, you can take a look at this file, and then you have the reference, for example, towards this, towards the pictures.
Yes and no. So for each real seed shell, for each single seed shell, you would have this kind of meta file, where we have the information this seed shell was produced on that machine at that date and so on. And then using these links here, I can pass back, check back. Okay, I want to know the machines where this seed shell was produced. Okay, then I find the other files, or at least I find the links. Here, I would only find that graph database. I would only find the links to the real file system on these sites. But for a single seed shell, I would have this file. For a single production run, I would have another file. For a single simulation, I would have here another meta file, short meta file here, so that you have a collection of single instances which are connected by these graphs here.
Okay.
And then you can really browse through that graph. If you're more interested in simulation, validation of simulation, then you would have a different perspective on the thing.
Okay. So this is also maybe an answer to my second question. Okay. So you have a lot of data, and how can companies benefit from it? Because I thought about when you're during your presentation, if you just want to optimize the process, you don't need so much data. But so you will go to a higher level, and then you can say, okay, you have this this production run, and you can take a look at these files and think about optimization of single parts of the production line. So you can okay.
So we will let it open what kind of application will be done. So it's like a maybe a specialized Google. On that level, we store as many as possible information and store also the connections between the different data parts. Some users are interested only in simulation, others are only interested in the, is my fiber good enough? And the other ones, like Daimler, they want to look on the details of the seed shell. So you can change your perspective, and then depending on your own perspective, on your own duties and tasks, you can start with your own point. Where is my fiber used, or who used my simulation model? And then you will find, using that graph table, you will find more and more links who directly or indirectly made use of your simulation results.
Okay.
You can change your starting point, can change your viewpoint, and then try to get more and more information from your perspective.
Okay, I have another question in the chat from Dr. Schulz, and he asks, is your digital twin activity linked to higher AR, VR systems like Holodeck from Fraunhofer Gesellschaft IIS? And there's also a link in the chat.
That would depend. That depends a bit on the type of data which we want to visualize. If you would have many of these 3D or big data, then it might be useful to, instead of using these standard visualizer tools, to bring these data into a AR or VR system, virtual reality system, or maybe if you have an AR glasses, something like that, to connect this user front end of AR front end to the digital twin. That means AR, VR, or simple visualizer are just a different types of user front ends which can make use of those data in the digital twin. So they are just different ways of representing data. They don't process the data. And so there might be many good uses for AR, VR systems, yes. But we haven't done this yet.
Okay. That's very interesting because I think, yes, you presented this screenshot, but I think this is not so interesting for you as a computer scientist because for you it's more important to have the process behind of this. Because I think this question was quite nice. If you, for example, you have a seashell which has mistakes in the structure, and you can have this. Lenses, and you can take a look at the seashell, and you can zoom and also pick up some areas, and maybe you can get the, what was it, ultrasonic pictures.
Yeah.
So this would be quite futuristic, but this is, as you said, it's just the front end, and the main music is in the back end, possibly.
Yes, but that's implementing front ends is also a heavy duty to do it.
Yeah, definitely.
And
definitely.
that depends what the user wants to see, and how the typical way of seeing things from a specific user perspective. There are many ways to do it.
Yeah. Okay.
Yeah.
Great. Do you have further questions? I think not for now, but I would suggest we made a screen recording. We will publish it, and like always, we will send an email. And I would suggest that I can put the contact data of Klaus Wolf into this email, if you agree.
It's fine.
And then if you have further questions, even afterwards, you can get into contact. And I think this is a very this is a great project, and I'm looking forward for the results. And I hope you will have a great demo day.
Yeah, thank you very much. We hope also that Corona let's do us those things in May.
Yeah, I hope so. Okay, so again, thank you very much for your presentation, and to the Fraunhofers, to the participants, thank you for your interest, and we will keep into contact. Thank you very much. Have a nice evening.
Thank you very much. Goodbye.
Bye-bye.
Thanks. Bye.